Just a minute. Just a minute. Thank you. So we're starting the 28th lecture. Yes, please.
What is the value of Vt is equal to 2 Vt or 3 Vt?
Hmm?
3 Vt. The problem is
Three. Vt means threshold voltage, not the thermal voltage. V capital T. We are considering now the effect of QF. I have found in the last lecture that due to the difference of work functions between phi m and the metal and semiconductor, the energy band bends, and as a result you have to apply the difference phi m minus phi f at the gate to make the energy band flat. So that is called a flat band voltage due to the work function difference, due to the finite work function difference. Now, effect of QF, this is a very important thing. You know, in a metal oxide semiconductor system, the oxide is a very critical place, very, very critical. So this is your metal, this is the oxide, and this is semiconductor. Say, I am always picking up P silicon. Now, within the oxide is found this, so let me write, this is metal, this is the oxide or any insulator, and this is P silicon, that means a semiconductor. Now, when you grow the silicon dioxide by the thermal oxidation technique, you see it's a chemical reaction which converts silicon into silicon dioxide. Si plus O2, 2O2. Si plus O2 becomes SiO2. And this, as a result, if you scan critically the interface region, the transition from silicon to silicon dioxide will not be an abrupt transition. In fact, there is a very thin layer adjacent to the interface within the oxide. This layer is called non-stoichiometric layer. Where the silicon dioxide is generally represented by a composition as SiOx. X is 0 here and X is 2 in the other boundary. At the silicon side of the non-stoichiometric layer, the X is 0, and the other side X is equal to 2. So silicon dioxide gradually grows from silicon to silicon dioxide. And then we assume that beyond that non-stoichiometric layer, that is stoichiometrically perfect layer, silicon dioxide chemical compound remains intact. Over this region, this non-stoichiometric layer, there will be many unsatisfied bonds. Silicon bonds. Silicon is a, the valency is 4, just like carbon, and all these bonds are satisfied otherwise. Covalent bonds are otherwise satisfied in silicon dioxide. But in this very thin film, thickness is around, let me tell you, this thickness is around 10 angstrom. This thickness of the non-stoichiometric layer is around 10 angstrom. Over this 10 angstrom layer, there are many unsatisfied bonds which are called dangling bonds. Unsatisfied or and these unsatisfied or dangling bonds, they trap charges. It is found that for a silicon dioxide system, the trapped charge at the non-stoichiometric region is fixed is independent of applied voltage. And this is usually called QF, or fixed oxide charge density. And for silicon dioxide system, this is always positive for silicon dioxide system. Whether the silicon is p-type or n-type does not matter. As soon as you grow this oxide on silicon at the interface, in the oxide side, a fixed positive charge is somehow induced or created. This is a process dependent charge. QF is process dependent. It is fixed. Fixed means does not depend on Vg. It depends on temperature and other things. It depends on the cut of the crystal. 111 crystal, QF in 111 crystal is more than QF in 100 crystal. If the crystal surface has an orientation which is 100, and if a crystal surface, silicon surface which has an orientation of 11, it is found the QF over the 111 silicon is more than the QF over 100 silicon. The reason is 111 silicon has more silicon atoms per unit area, the surface density of atoms, as compared to 100 silicon. Each atom contributing one electron or one charge makes QF more for more packed surface as compared to less dense surface. QF depends therefore on the packing density of silicon atoms on the surface. Less is that packing density, less will be the value of QF. Therefore, from device point of view, 100 silicon is preferable to 111 silicon. And there is another reason already mentioned earlier, the scribing and breaking is more convenient for 100 rather than 111. Therefore, in production today, nobody uses 111. All VLSI production is based on 100 wafers. Now, because of the positive charge, that means at the interface, you just see, at the interface, it is 10 angstrom thickness means practically it is at the interface, 10 angstrom is really very, very thin compared to the gate oxide thickness. So practically this is the interface. So at the interface, we have a good number of positive charges which are immobile, static, and which is constant in nature, does not depend on the applied voltage. This is my QF. And what will be the effect of this QF? In the case of P silicon, this positive charge will attract electrons and repel holes. Even if I do not apply any gate bias, if Vg is equal to 0, because of the presence of plus QF, a depletion layer will be created automatically. Because of the presence of the positive charge, a depletion layer will be created. Even with Vg is equal to 0. And the positive charge sometimes is so strong that even an inversion layer is created. And that happens quite often. Because of the undesirable positive charge, which is a result of production, fabrication, is a process dependent thing, quantity. The surface sometimes remains inverted, even with 0 gate voltage. So if I make such a device, an NMOS, that is, we place an N plus here and N plus here, what will happen to this device? When Vg is equal to 0, the device will conduct. Such a device will naturally come as a depletion mode MOSFET. In fact, that was the difficulty of NMOS technology in the beginning of MOS technology. traditionally, say bipolar transistors, I do not know whether you know the history or not. Traditionally, bipolar transistors, when it came and commercialized, it was mostly all PNP transistors. Then it gradually became NPN. That are the fabrication things. Similarly, MOS technology, MOS theory was known even earlier than the other things. But technologically, MOS came later. At the end of at the end of 60s, the proper MOSFET came. In fact, MOSFETs as a VLSI or LSI circuit came at the end of 50s, just around 62, 63, in that period. About 10 years after about 10 years after the bipolar junction transistors invention, the MOSFET came commercially. And those MOSFETs which came, they are all P MOSFETs, particularly for IC fabrication, called MOS LSI. The reason is, if it is N-type silicon, what will happen? The fixed positive charge, what will be its role? Yeah, it will keep the surface in accumulation. If it is N-type, the positive charge, more electrons will be drawn here. The surface will have more electrons than the bulk. The surface will remain in accumulation. So the device will be normally off. And therefore the transistor will be enhancement mode transistors. And I think you know that in MOS inverters, all VLSI or that MOS integrated circuits, the driver must be an enhancement mode device. Otherwise, there will be input-output compatibility problem. The output of a MOS inverter should be able to drive another similar MOS inverter. That will not be possible if the driver is a depletion mode MOSFET. So from application point of view, enhancement MOSFET was essential. Without enhancement mode MOSFET, one cannot make a good circuit. Unfortunately, when NMOS technology first came, because of the problem which I have just now told you, because of the fixed positive charge, the surface remains inverted quite often. And that will keep the device in normally on condition, which is not desirable. Maybe the driver, the load may be nowadays that is needed. The load transistor of the inverter should be rather a depletion mode device. But the driver transistor must be an enhancement mode device. And that was a practical difficulty. So initial days, about the first 5 years of MOS technology development, it was entirely dominated by PMOS. Knowing fully the NMOS is superior so far as speed point of view, so far as transconductance point of view. But then the problem was solved by channel implantation and other techniques. And once it was solved, NMOS technology came up. PMOS was sidelined. PMOS was totally sidelined for about 10 years. The entire market was dominated by NMOS only. But then CMOS people thought, because the density was increasing, power dissipation became a very, very important point. CMOS came back. CMOS philosophy was known, the principle was known, but it came back and automatically P-based PMOS also returned. Now people tried to see how I can make devices, both NMOS and PMOS, which are optimal in performance. Now because of this QF, what is going to happen, therefore, the energy band again will go bend downward. Am I correct? Because of this fixed positive charge, what will happen? The energy band, because the positive charge that means the same effect as you are doing with the help of a VG, positive VG, you are producing the same effect by positive charge. So you need an extra negative voltage at the gate to nullify that effect. So you have to, your VFB due to finite QF, but assuming that phi ms is equal to 0. Flat band voltage due to the finite QF, under the assumption that the difference of work functions between the metal and semiconductor still remaining 0, is simply equal to minus QF. You can easily find it out. Therefore, the total flat band voltage which arises due to, I can call it flat band voltage for phi ms non-zero but QF 0 plus the flat band voltage due to QF non-zero but phi ms 0. The two, sum of the two should be the actual flat band voltage. Therefore, the actual flat band voltage is given by phi m minus phi s, which is sometimes written as phi ms minus I have written like this to avoid confusion because UF is always positive. Otherwise, I should not have given this modular sign. In practice, you don't put the modular sign. If you are quite experienced, sometimes in certain cases the QF may be negative. Bare silicon has a negative QF. Bare silicon or nitride grown on silicon have a negative QF. In that case, better to not to. But because most all under 99.9999% cases, the oxides are dielectric. Therefore, I have kept it like this. This is easy to for your formula, for your computations from you. Therefore, actual flat band voltage, which is the sum of this flat band, actual threshold voltage, is sum of the flat band voltage and Vt under the assumption that the flat band voltage is 0 and is given by therefore VFB plus 1 by Ci Okay, is it okay? Okay, now therefore you are able to compute the value of the threshold voltage for ideal condition when flat band is 0, flat band voltage is 0, as well as for the practical case when flat band voltage does exist, okay? And in that case, therefore, I'm asking you to repeat these two problems by finding the values of VFB. Like here I asked you to calculate the Vt values, then I did not introduce the concept of VFB. Now I introduce the VFB and compute VFB and hence also calculate actual Vt actual with the following information. You assume that aluminium phi m is 4. Okay, there is no need. Already things are known to you. Phi ms you can easily calculate from this. Only thing I am giving you the value of QF, which is equal to 10 to the power 10 electronic charge per centimeter square. This is a variable quantity. It may be a process dependent parameter. If you can achieve 10 to the power 10 is good. On 111 surface, QF may be of the order of 10 to the 11. Whereas for 100 it is 10 to the 10 or sometimes even less. The less the value of QF, better is more desirable it is. One thing I have just ignored so far, the effect of interface traps. In the interfacial region, in the interface of the oxide silicon at the silicon silicon dioxide interface. The semiconductor band structure, energy band diagram looks like this. But then in the band gap, it is not a completely empty band gap. Because of the transition from silicon to silicon dioxide, the band gap will have now lot of allowed states. Otherwise, band gap is a forbidden gap. In the bulk of silicon, this band gap should be an ideal band gap, an ideal forbidden gap, excepting for the donor levels, or which are not shown here, acceptor level, etc. There are acceptor levels close to the valence band because it is p-type doped. If it is n-type doped, there will be donor levels close. Otherwise, this band should be empty. But at the, I've already discussed earlier in the very beginning of these lectures that there may be some allowed energy states in the band gap due to two things. One is undesired impurities. They introduce some kind of traps in the band gap. And these traps are sometimes also called the recombination center. Through these traps, actually recombination generation takes place in silicon, germanium type of materials, predominantly. Similarly, there are imperfections in the lattice. If the semiconductor is not a very good quality crystal, due to the imperfections, which introduce aperiodicity in the structure. All these things come because of the periodicity of the lattice. Chronic penny metal, like kind of model, where periodicity is a very important thing. But any aperiodicity, variation from periodicity, introduced through impurity atoms, introduced through imperfections in the lattice, will induce energy states. These are bulk energy states. Even in the bulk of the semiconductor also, the band gap will not be a perfectly free or empty band gap. There will be some states. And through them, the traps, the recombination becomes enhanced. Generation recombination process becomes enhanced. I have discussed, in fact, I shortly read Hall recombination is nothing but recombination through these trap states. But as you come to the interface or at the surface, because the lattice is suddenly truncated, what is going to happen? Your chronic penny model, which is based on ideal periodicity, is suddenly hampered. It's called semi-infinite solid. Semi-infinite. Otherwise, if it is infinite, the periodicity extends in plus x direction, minus x, plus y, plus z, minus z. But in this case, if the x is perpendicular to the surface, as we approach x is equal to 0, suddenly the periodicity is lost. And it was analyzed by the physicists, and they found in such cases of semi-infiniteness, the general band structure remains the same, excepting a lot of energy states are introduced in the so-called forbidden gaps. All these forbidden energy gaps are now flooded with many energy states which are not as dense as those in the conduction band, valence band, and other allowed bands. They are very dense and practically continue. Whereas in the band gaps or forbidden gaps, there will be states, they are dense at the same time, they are not as dense in EC, conduction band and valence band. So what is going to happen, there will be many energy states like this here. Like this. And this energy state density, which is the corresponding plot of DIT. DIT is called density of states, interface states. IT stands for interface trapped charges. IT, interface trapped. So DIT against energy, electron energy, is a plot something like this. It is a plot of DIT versus energy. So it is usually found that because of the interface states, the energy states which are introduced in the band gap, they are very fast in nature. Let me tell you, they are very fast, which I also discussed earlier. You know that if you uniformly radiate illuminate a semiconductor piece and suddenly withdraw the source of illumination, the excess electron holes start recombining. But recombination is faster near the surface as compared to the bulk, which I explained earlier. You may remember it. So these interface states are quite fast, faster than the normal generation recombination lifetimes. It is very important. Now, what is going to happen? Can you tell me? Because now there are a lot of interface states like this, as indicated here. Only the density of states is less near the center and highest near the edges. That's how I have plotted. You have seen? Is minimum near the center of the band gap and high near the edges. Now, you see that the Fermi level is located here. So what is going to happen? Can you tell me? Up to the Fermi level, according to our Fermi-Dirac statistics, up to the Fermi level, all the states will be occupied. Above it, it will be empty. At T is equal to 0 degree Kelvin, that is perfect. Even at 300 degree Kelvin, semi-perfect, which I discussed earlier. So up to EF, all states will be filled up. So there will be some electrons. Earlier we thought that there cannot be any charges here, excepting the traps, the bulk traps, which are very much localized usually. The bulk induced traps are highly localized. Whereas interface traps, they are continuously distributed. Not continuously in the mathematical sense, they are also states. Their density is far less than that in the conduction band or in the valence band. But still they are much higher than normal case. So what will happen? Up to Fermi level, all the states will be filled up with electron, and there will be some extra charge, which I call it QIT. So up to this, all the states will be filled up with electron. Let me magnify this portion now. If this is the Fermi level, and this is your valence band, there will be a lot of electrons occupying these states. Each state can accommodate 2 electrons of opposite spin, is known to you. So there will be a lot of electrons here. Considering that these are spin, and that will contribute a QIT, which will be negative because dominated by electrons. This QIT concept we have never introduced in our analysis so far. But will it affect? Because when you remember the case, when you are changing Vg, the position of Fermi level at the surface is also changing. Under flat band condition, the Fermi level at the surface in the same position as in the bulk. But as you make it accumulated, the Fermi level comes closer to the valence band edge for p-type semiconductor. As you deplete the surface by applying a positive voltage and surface becomes intrinsic, the Fermi level at the surface comes at the center of band gap. And as you invert the surface by applying a large gate bias, more than Vt, the Fermi level comes closer to the conduction band edge. And that's how there are more electrons at the surface than the holes at the surface. And if the Fermi level position is shifting like this, then QIT is also now should shift. Therefore, QIT, this quantity which I ignored earlier, is a function of the position of the Fermi level at the surface, and hence it should also be a function of the applied Vg or surface potential, whatever we call it, same thing. Is it all right? And this QIT can be written as, in terms of density of states, as Q into DIT D from EV to EF. Is it all right? QIT is DIT. What is the unit of DIT? Per centimeter square per electron volt. DIT is per electron volt per centimeter square. Per unit area of the surface, per electron volt of energy. And therefore you multiply by D, okay, and integrate from EV to EF, multiplied by Q. You should get the value of QIT. And from there you can write DIT is equal to 1 by Q dQ. Now in the MOS analysis, now so far as the MOSFET calculations, the derivations so far it introduced in the class, what are the charge components we have so far considered? Charge in the depletion layer, charge in the inversion layer, and let us just before 5 minutes ago, we introduced charge in the fixed, that non-stoichiometric layer, which I called QF. And I have considered them, and that's how we finally obtained an expression for threshold voltage, which contains QF, which contains QD, QS, as well as these are the two components of charge. But then now I find, and fortunately that QF was not dependent on threshold Vg, but this unfortunate quantity QIT is a very much function of Vg. Is an additional charge, negative charge. So what is going to happen now in your CV plot because of this thing? Can you tell me? This is a very interesting thing. Some of you should be able to suggest. First, let me see what is the effect of the flat band voltage. We have so far not considered. The C versus V plot, which I initially drew, the ideal curve was like this. The ideal CV. This was CI and this was CFB. I'm not rewriting here. CI and CFB. But this assumed the condition of flat band. So now the flat band has been introduced. What would be the typical, say in the case of NMOS, what is the expected flat band voltage, negative or positive? In our NMOS case, the quantity which I have just now, and I have given you the problem also, what will be the sign of VT, VFB? Negative, because phi m is less than phi s, you already noted, and this quantity itself is negative, I have told you. So it will be a negative quantity. So effectively, therefore, my actual curve shifted now. Let me now, okay, I'm drawing it like this now. The curve is expected to be as if this whole thing now this is the ideal but considers VFB. I should have drawn oppositely. I should have made this curve broken and that is solid, because this is a practical curve I expect. This is ideal, does not consider and if you take this a simple formula of W etc. and do the plot, you will find the same curve but up to this only, from here to here. But beyond this you cannot calculate from that point. Is it alright? Now all these plots did not consider QIT. Now consider the case of QIT, which is function of voltage. Higher is the VG, more is a depletion layer. What you are doing, you are shifting your Fermi level from the valence band edge to the conduction band edge. Gradually QIT will increase, negative charge, more and more negative charge. So what will be the effect as a result? Capacitance increases. And we expect, let me tell you, really speaking, we expect a curve something like this. And suppose you are taking the high frequency measurement, what will be the kind of curve we expect? Now, high frequency CB plot. Yeah, right. Constant, minimum or slightly. That is a literal, So this will be the measured high frequency. And had you noted that two things I think I should have elaborated to you. How I have defined VFB? Is the cutting point in point of intersection of CFB. Okay? It is a voltage at which the capacitance is the flat band capacitance. That's how normally the CFB, we get the value of VFB. And because of this effect, this will be also a little bit shifted. And at every voltage, there is a stretching of this curve. That firstly, there is an overall linear shift. The ideal curve got shifted to the left by the amount which is VFB. Either to the left or to the right, depending on the polarity of VFB. This was the first thing. But that did not consider the effect of QIT. Considering the effect of QIT, not only the curve will be shifted to the left or to the right, but also the shape will be a little bit distorted, broadened shape. Stretching. This is what is known as the language of MOS physics, called stretching of the curve. Stretching of the curves. And this stretching, amount of stretching from the ideal curve, which you can easily plot. The ideal curve you can always calculate and find out. You first measure from experimental value data what is the value of VFB. And in that case, these 2 points will be the same. Do you follow what I mean? How to find the value of VFB? How to find the value of VFB? Experimental VFB will be this point. Am I correct? Because you are taking the CV plot with the help of some experimental technique. Okay, so then you find out at which value the capacitance is CFB. CFB you have to calculate. You get VFB. But here, I have shown it separate. Actually, what should I have done? I have assumed the same value of VFB for both the curves, which I have not done here. As a result, what is done actually, we assume stretching is taking place like this. Do you follow? But here, because I have explained first VFB, shifted the curve, and then brought in the case of, but actually CV is obtained from measurement only. And otherwise, there is no way of finding VFB. I have to find the CV characteristic by experimental technique, then compare with the ideal plot, find out how much is the shift, and that shift will give me the value of CFB, that VFB, the flat band voltage. So therefore, as a result, the way I have shown two flat band voltage is not correct. In fact, I should have shown it like this. But thereafter, I find that my curve, which I get experimentally, really does not match exactly with the kind of curve which I am getting theoretically. Rather, there is a little bit rounded, a little bit flattened, stretched. And if I can note down the amount of stretching at different values of voltage, what information I can extract? DIT or QIT. So I will request you to take this, because I am not going into the details of this thing. I will request at least the physics oriented boys, our physics department people, as well as some of us, our students who are interested in some physics persuasion. I request them to go into the details of this, how to extract the density of states versus this curve, whatever I have plotted here, called density of states distribution in the energy gap, and the corresponding lifetime of the different states, how to obtain that from CV plots. And I am plotting another thing called GV, CV and GV. CV and GV. GV means conductance versus voltage plots. From these two plots, how to get DIT versus energy. This is energy. And the lifetime of these states, lifetime of these energy states versus E, again energy. This is a problem for those who are interested in academic persuasion on device physics. It's a very important topic. You'll find that this CV technique is so popular, CV and GV techniques are so popular for characterization of semiconductor interfaces. And there is a technique called DLTS. I do not know, any one of you have heard of it or not? Can you expand? DLTS? This stands for deep level trap spectroscopy. Deep level trap spectroscopy. It is a very important tool for semiconductor surface characterization, and is based on the CBGB plots. Deep level trap spectroscopy is just like any other spectroscopic technique. It's one of the popular techniques, purely electrical in nature, and gives a lot of information about DIT and tau, particularly the deep levels, which are very, very fast. I told you, the deep levels means, what are deep levels? Near the band gap center. They are very fast. And you must get some more precise information about them. And for that, DLTS is a technique which is very, very popular. Okay, before closing today, I'll just introduce one thing. You know the MOS capacitor equivalent circuit. Can be shown as like this: CI in series with CD. Is it not? But don't do that. You little bit modify it in the light of our density of state, QIT effect. What you do? Yes, I keep CD. But then in shunt with CD, let me bring a R and a C. This is the typical MOS capacitor. This R I called RIT, and this C I called CIT. You know that extra thing, the charge, QIT will list additional as additional capacitance, and that additional capacitance must appear in parallel to CD, but in series with CI, definitely. But then these capacitance is something like dynamic ones. They are not the ordinary static linear capacitance. They are dependent on voltage, and they are also, they are time varying in nature, because once electron go there, how long they will stay there or jump back, that depends. That is also characterized by the lifetime of those states. Therefore, that to bring the lifetime into the picture, I have introduced RC. It's a very convenient one for the electronic engineers who can model any physical system which is time varying through RCs. In mechanical systems also. Any physical system. A river, for example, can you tell me, a river, a bank, the river, there is a, suddenly there is a dam type of structure. There is storage of water. You put a C there, capacitance there. There is a channel, very narrow channel in the river. You put a resistance in series. There are certain soaking region where some water is coming out. You put a G there, conducting path. Like this. Somewhere the water getting idling out due to some toroidal motion. You put an L. Inductor is nothing but an idler device. And that is done in equivalent circuit. You know how the speakers are represented. Any acoustic systems can also be represented by electromechanical equivalent circuits in terms of L, C's, R's. Exactly that thing I have done. To bring in the concept of lifetime, I have brought in the RC. Then what you do, you simply redraw it once again. You draw it like this. This is the same CI, but now I call it some, that CP, the parallel. I convert this circuit into effective parallel circuit. I call it GP, where CP can be easily found out to be CD plus CIT divided by 1 plus omega squared tau squared, and GP is equal to CIT omega squared tau square, where tau is nothing but the so-called lifetime or time constant. You see that when I ignore the effect of CIT, the second term, this term becomes 0, so it becomes simply CD, and this term also becomes 0, means this is eliminated. Conductance 0 means open circuit. But the presence of this interface states is modifying our circuit. Can you just tell me some kind of things coming to your mind from this expression? You see that both CP and IGP now is modified, and that are because of the presence of RIT, something is happening. A frequency dependence is coming. If RP was there, RIT was not there, this frequency dependence would not have come. So you can perform the experiments therefore at different frequencies. The CV plots or GB. Now you can do GB also. You can understand the present now GB, isn't it? What you do, you find out the impedance of this. Subtract the reactance of CI from there. Then you get the impedance of this. Convert the impedance into admittance. Take the real part, you get this. And take the imaginary part, you get this. You understand? It's a very simple thing for electronics. Let me repeat. You find out the impedance. subtract the reactance of Ci to get the impedance of this, find the reciprocal to get the admittance. It will have a real part and imaginary part. Real part is this, imaginary part modified from by divided by omega is this. And you can do it for different voltages. You measure the CV, you measure capacitances at different voltages, and from there you extract the value of Cp and Gp at different voltages. And also you can do it at different frequencies. Now my interest is to determine what is the value of DIT or QIT, as well as what is the value of tau at different positions in the band gap. So I am giving you this much information. The next task is to, for some of you, not for all of you, because everybody may not be interested in this kind of task. I request you to go through that CV techniques and GV techniques for characterizing semiconductor surface. It's a very important technique. I am giving you just the very beginning of the whole thing. Very interesting technique.